Welcome to The Explainer. Today, we're going to decode the ultimate complex machine, the human body. More specifically, we're looking at the biological engines that drive absolutely everything we do. Without our muscular system, we wouldn't just be frozen in place. We literally couldn't digest our food, circulate our blood, or even stay warm. It is an incredibly dynamic system, and today, we're going to break the whole thing down.
Okay, do me a quick favor right now. Just smile. Simple, right? But beneath the surface, that single, effortless action requires a highly coordinated symphony of biological levers and pulleys. The sheer complexity of everyday movements is honestly mind-boggling when you realize that hundreds of distinct structures have to contract, stabilize, and relax in perfect harmony just to let you blink, take a breath, or express joy.
Okay, let's dive into this. Here is our roadmap for today. We're going to start at the cellular level with muscle tissues, work our way through the mechanics of movement, decode some of that crazy anatomy jargon, and then finally map out the axial and appendicular divisions of the body.
Section 1. Meet your muscle tissues. These are the foundational cellular blueprints that make it all possible.
The body actually utilizes 3 distinct types of muscle tissue, and each one has its own unique cellular blueprint. First up, we have skeletal muscle. These are made of very long, multinucleated cells that feature distinct cross striations, basically striping. Next is cardiac muscle, which is found only in the heart. It also has those cross striations, but the cells here are branched and they're bound together by structures called intercalated discs. That is a feature totally unique to cardiac tissue. And finally, we have smooth muscle, which is made of fusiform cells. Those are essentially spindle-shaped cells that completely lack those striations.
Now, the architecture of these cells directly dictates how they behave. Skeletal muscle provides quick, forceful contractions, and crucially, it's entirely under our voluntary control. You consciously choose to move your arm, right? But on the flip side, cardiac and smooth muscles operate strictly on autopilot. Smooth muscle gives us slow, involuntary contractions to move substances through our organs, while cardiac muscle delivers involuntary, vigorous, rhythmic contractions to pump blood relentlessly throughout our entire lives.
Section 2. The mechanics of movement. So, how do these microscopic tissues actually manipulate the skeleton to create movement? And this brilliantly illustrates the basic mechanical principle at play here. Every skeletal muscle features a few key parts. The belly is the fleshy, contractile part of the muscle. This belly is anchored to your bones via strong, rope-like connective tissues called tendons. Now, when a muscle contracts, it pulls a movable bone, which is the point of insertion, towards a stationary, fixed bone, which we call the origin. Think of the origin as the anchor and the insertion as the piece being reeled in.
But here's the thing. Muscles rarely work alone. They operate a lot more like a highly coordinated sports team. For any given movement, you've got the agonist, or the prime mover. This is your star player, mostly responsible for producing the movement. Opposing it is the antagonist. That's a muscle whose action directly opposes the prime mover to provide control and tension. And finally, we have the synergists. These are the absolutely crucial supporting players that provide additional pull and help the larger agonist work efficiently.
Let's look a bit closer to see how this builds into an even more refined system of control. Within that group of supporting players, we have a specialized type of synergist called a fixator. Fixators are absolutely vital. They assist by preventing movement at another joint, effectively stabilizing the origin point. Because without fixators anchoring your posture, the prime mover would just waste energy pulling both ends of the skeleton at once, instead of creating a clean, targeted movement.
Section 3. Decoding muscle names. It's time to translate that intimidating medical jargon into a logical, secret language.
Anatomical naming is really just a highly descriptive code. Muscles are generally named by their action, origin, location, or some combination of those. For example, a flexor simply decreases a joint angle. The word biceps tells you the muscle has 2 origins, or tendons of origin. Temporalis is a giant location clue. It's a muscle found right over the temporal bone of your skull. And what about the mighty sternocleidomastoid in your neck? Sounds completely terrifying, but that name literally just lists its attachment points, the sternum, the clavicle, and its insertion on the mastoid process. Once you know the code, it really is just a fun puzzle.
Section 4. The axial muscle division. Let's transition to the macro view and look at the body's structural chassis.
The skeletal muscles in our body are split into 2 main divisions. And get this, a massive 60% of all skeletal muscles belong to this axial division. These muscles arise directly on the axial skeleton. Their primary jobs aren't about reaching or walking. Instead, they're tasked with stabilizing the head, positioning the vertebral column, and moving the rib cage so we can actually breathe.
Now, what's really interesting about this slide is the incredible contrast between two major muscle groups right on our head. On one side, the muscles of facial expression. These are super unique because they originate on the skull, but they insert directly into the superficial fascia and dermis of the skin. They move the skin itself so you can smile or frown. On the other side, the deep muscles of mastication or chewing, like the powerful masseter, insert directly onto the mandibular bone. They don't move the skin. They pull with immense force to elevate the jawbone so you can crush your food.
Just to quickly summarize the sheer variety here, the axial division handles our head and neck, managing everything from our extrinsic eye muscles to the intrinsic muscles that alter the shape of our tongue for speaking. It also includes the complex layers of the vertebral column for back extension, the broad muscular bands of our trunk like the obliques and rectus abdominis that form the walls of our core, and of course the pelvic floor muscles that span the pelvic outlet to support our vital organs.
Section 5. Moving the limbs. Now we move outward from the core to explore the levers of our biological machine. So if the axial division was 60%, the appendicular muscles make up the remaining 40% of our skeletal muscles. Their sole purpose is to support, stabilize, move, and brace the appendicular skeleton, meaning your arms and legs. These are the powerful biological levers that allow us to interact with the world, to run, to jump, and to lift.
Let's look at a prime example in the upper body, the deltoid. This large triangular muscle is what gives the shoulder its rounded contour. But it's remarkably versatile because it has three distinct sets of fibers. The anterior fibers flex and medially rotate the arm to let you reach forward. The middle fibers are your primary abductors, letting you lift your arm straight out to the side, and the posterior fibers extend and laterally rotate the arm, so you can reach backward. That's three totally unique actions from one incredible muscle structure.
Moving down the arm, we find the famous biceps brachii, which, completely true to its name, features a short head and a long head. Go ahead and flex your arm real quick. We usually think of the biceps purely as an elbow flexor, but surprise! Its primary function is actually supination, which is the action of turning your palm to face upwards. Flexion of the elbow is absolutely a major function too, but it shares that spotlight with its synergists.
Down in the lower limbs, the appendicular muscles really scale up in massive power. The gluteus maximus is the most powerful extensor of the thigh, absolutely essential for climbing stairs or rising out of a chair, while the gluteus medius provides critical pelvic stabilization when we're walking. Further down, the soleus muscle in your calf is a total powerhouse for plantar flexion, which is pointing your toes. Because the soleus doesn't actually cross the knee joint, it's highly active, just keeping us stabilized so we don't fall flat on our faces when we're standing quietly.
So the crucial point is, why do we care? Why does understanding the exact depths, origins, and bellies of these muscles actually matter outside of a biology classroom? Well, this isn't just trivia. Mapping the muscular system has profound daily applications in healthcare and medicine. Consider the intramuscular injection. Healthcare providers have to intimately understand muscle bellies, like the deltoid or the gluteus medius, to deliver medication safely. Deep muscle injections are preferred over superficial ones when a patient needs really prompt absorption, when they're administering larger doses of a drug, or when a medication is simply too irritating to be delivered into the delicate subcutaneous tissue just beneath the skin. Knowing exactly where those muscle fibers sit is literally a matter of patient safety.
From the microscopic intercalated discs of your beating heart to the massive pulling power of your gluteus maximus, your muscular system is just a marvel of biological engineering. You have hundreds of muscles constantly communicating, stabilizing, and firing just to keep you upright and moving through the world. So I'll leave you with this. Now that you understand the hidden mechanics behind your every single move, how will you fuel and treat this incredible machine tomorrow? Keep exploring, keep moving, and thank you so much for joining me on this explainer.